to our next tech talk. This tech talk is, can specialized AI chips solve my AI productization challenges? So please welcome the man with all the answers, Nick Nee, Director of Product Marketing for AI, Software and Ecosystem at Xilinx. His team's responsibilities include product, go-to-market, business development, and Alliance ecosystem program management. So Nick earned a master's degree in computer engineering from UOT, so University of Toronto, and holds 10 patents and publications. So Nick, how are you? The stage is all yours.
All right, hopefully you can see me and
Yes.
hear me. Okay, now the challenge is see if I can share my screen. Let's see. All right, see my screen? Okay, perfect. All right, so I'm assuming you can see me and hear me. Hello, everybody. Good morning, good evening, good afternoon, wherever you are. So thanks for the introduction. My name is Nick Nee. I run product marketing team for AI, software, and ecosystem for Xilinx. So today I'd like to kind of switch up a topic a little bit, focus a little more on how to productize and commercialize AI solutions from the hardware perspective, because that's actually becoming one of the very hot topics and also very challenging topic, because all of you, right, many of you have really great ideas on AI and how to optimize algorithms, common sense, etc. But the bottom line, how do you really productize that, putting this onto some commercial hardware that has the right power, right cost, right performance, right latency for your edge or data center application is really where the productization and monetization hits the road. So from that perspective, I want to first kind of give you a sense of how challenging it is becoming. With all that artificial intelligence and deep learning, the compute requirements are really becoming orders of magnitude more compared to traditional computer visions or SLAM and machine learning techniques. So CPUs, long gone, right? I mean, it's already not scaling as fast as we would like to, in terms of frequency. And then the fixed hardware accelerators does a really good job for commodity use case, but not for something that's fast changing like AI. So the domain-specific architecture, right, is really where we need to go. And this is, something that Hennessy and Peterson have coined as a term. You have to have a domain-specific special architecture for your particular workloads that's demanding, such as AI. So TPU from Google, DLA from NVIDIA are already doing this. And in fact, Xilinx has adaptable hardware, which, it's called FPGAs, and that you can basically reprogram your computer architecture for your particular AI workloads. So let's look at what is DSA, or domain-specific architecture for AI. And there are really three main things that need to be customized for every network that you invent. And first thing is data paths, right? Every neural network has different way of passing data, and modern networks are getting more and more complex. Precision, right? Used to be people use 32-bit floating points, now became 16-bit, and today 8-bit integer is pretty much the state of the art. However, now the research is moving this even to more mixed precision or even lower precision at the 1-bit, 2-bit, 4 bits. So every neural network really has different type of sweet spots in terms of precisions. And then finally, one of the most difficult things, feeding the beast, right? It's getting easier and easier for somebody to build a hardware that has tens or hundreds of teraops or even petaops these days. But the difficult thing is how do you pump the data for these engines to keep processing? So, moving the data so that the engine always has work to do and keep it 100% busy is next to impossible task. And in fact, if you look at MLPerf or some of the standard benchmarks, most of the GPUs or ASICs are really hitting very low utilization in terms of when you compare with the vendor data sheet peak tops. So being able to customize the memory hierarchy to feed data into the hardware pipeline is extremely critical. Now with that, I think all of you know very well that AI neural networks are expanding significantly, right? Every model has innovations happening and the application area is expanding. even if you look at each of those models, again, something I'm sure you know very well, innovation has been significant. Just to do the same classification, starting from AlexNet in 2012, and nowadays MobileNet, DenseNet, there's lots of different, more complex but more accurate models that came out. And just to kind of illustrate my points, right? If you look at some of the two extremes, back in AlexNet 2012, the neural network was really relatively simple, right? Like everything was feed forward. You do a convolution, you do a polling, and then you basically feed the results to the next layer. But a year later, Google came up with GoogleNet, which already made the topology and the memory hierarchy much more complex. And then nowadays, the DenseNet, MobileNet, depth-wise convolution makes it actually skip through. So your result has to be buffered and kind of put it into, like, let's say 10 layers ahead. And that kind of puts so much stress into the memory hierarchies, caching systems to make sure your data is always available. So basically, you really need a completely different, almost three different hardware architecture to support each of these neural network efficiently, and to close to the 100% utilization. And doing this with a one single architecture is next to impossible. And this is where the DSA is required. You have to have a different type of architecture for different group of neural networks to get most out of it. Now, of course, GPUs and ASICs will take the custom chip route, right? In order for you to support the latest topology, you have to basically retape out your chip and come up with a new one, which takes years. Where the FPGAs, can simply use the same chip and reprogram with your new architecture for your latest neural network. So we've actually recently proved this point, and actually the results just went live yesterday, I believe. Latest MLPerf inference benchmark has proven that we can do the highest so-called highest peak tops. What that means is based on the amount of data sheet peak we have, you can get the highest real tops on the benchmarks. And this is a really good measure of how much you can utilize on the real hardware. So given, let's say you have 100 teraops hardware, if you can do 80 tops on the ResNet, that means you're getting 80% out of the 100% peak. And for us, we actually achieve 100% efficiency compared to our data sheet, because we were able to create a domain-specific architecture for each neural network, which is most optimized. And another really cool thing, just to kind of demonstrate my point, precision, right? Precision is getting, there's all sorts of research that's pushing the precision to lower and lower, and also mixed precision. And let me show you how this impacts, platform like FPGAs. If you do an 8-bit multiply and accumulate for your typical neural network, let's say it takes this much area, right, to do your Mac. Now, if you can turn every multiply and accumulate into 4-bit, suddenly you save quarter of the area, right? You can only do this with a quarter. That means you can cram 4x more compute. Now, if you can go binarize neural network, 1-bit, we further shrink the area to do this by 10x. What that means, I can use one single 8-bit multiply and accumulate area to do this much 1-bit operations. And suddenly my peak, which, one of our latest 7-nanometer device is 140 tops, and the NVIDIA T4 is 130 tops. So at 8-bit, we're about the same. But using the 1-bit, suddenly the peak goes up to 1 petaops. And this is the kind of power, most of the GPUs and AI ASICs are basically designed for certain precisions, most likely 8-bit or floating point 16. But when you try to do something more lower precisions, it doesn't actually benefit them. But FPGA, because you can create the DSAs for your custom precision, you can really raise the ceiling as well. And one last point I want to make is, in productization, non-AI is as important as AI. So any AI application is much, much more than AI. And just two simple examples: smart retail, right? In the middle box, you have AI inference, where you do person detections and object detection, etc. But before that, you have hundreds of streams of video coming in, let's say encoded in H.264. You have to first decode them in the very parallel and fast fashion, And then you feed into computer vision to do, say, resizing, make the size right for your CNN. Then you finally apply your deep learning. And then after that, you still have to track your user based on some traditional computer vision. And then you also may have to encode it out into different resolutions depending on your end user's cell phone or HD TV or 4K TV. Automotive, right? It's another very obvious example. Before AI can process, you have to have a lot of fast processing down on the sensor fusion. You have many cameras, lidars, radars. Those have to be processed in a conventional way. Then you apply AI for, say, segmentations and object detections. And then all the way post-processing, you have to go to actuator, hitting the brake, turning the wheel. It's that end-to-end latency that's absolutely critical, right? So even if AI, some chip is really good at AI and makes the AI time really short, you're still not hitting, in many cases, the end-to-end throughput, end-to-end requirements, because that's what end user cares about, right? And what you really need to do is to have a domain-specific architecture for every part of the workload and then be able to optimize at the system level, at the data flow level. And that's really the only way you can achieve something very aggressive like 30 millisecond end-to-end latency, for example, for automotive. And this is the area where, for example, a company like Xilinx is really well proven, even before deep learning became very hot. Companies are seeing the huge value in being able to optimize at the hardware level different applications, different workloads, and hit the end-to-end requirements is really the value that people are choosing as. So recently we had a number of good public success. For example, Pony AI is one of the world-leading autonomous drive company. They're using FPGA. Every pixels and every sensors go through FPGAs, and then they can see a much shorter latency and determinism, which is very critical for detecting corner cases like this. We've just announced with Subaru joint press release, and they're using us in their latest EyeSight, which if you have a Subaru car, you probably know what I'm talking about. And this saves a lot of lives using computer vision and deep learning. And then speech recognition, SK Telecom is a big hyperscaler in South Korea, and they're using personal voice recognition devices, and then in the data center they're using us for the speech recognition type of process. And then for LiDAR, Ouster has also made a press release with us, and they're using us for signal processing as well as the backend. So with that, hopefully you kind of saw that FPGAs and adaptive computing platforms are very important, especially when the AI is moving so fast and very challenging. But there's one key challenge we have to solve, which is enabling AI scientists like you. FPGAs, right, is traditionally known as something that you need to have a hardware or electrical backgrounds. Now, that's no longer true. With the investments in the Vitus AI, which is a product we launched that can take directly TensorFlow, PyTorch, and Caffe models and compile this directly into optimized FPGA implementation. So this one, just like how you would do this on CPUs or GPUs, you can take your trained model in TensorFlow, compile this in seconds to minutes, and then run this on one of the predefined boards we have. And we actually have different type of domain-specific architecture optimized for CNN, LSTM, MLP, MBERT, etc. So you basically don't have to be a hardware expert to utilize and realize the benefit of FPGAs. Okay, just to kind of wrap it up. So AI productization really requires a domain-specific architecture, especially now. Performance, latency, cost, all that requirements are still very harsh. And while you have to have order of magnitude more compute, and that's when you have to have a specific AI optimized hardware architecture. Now, only adaptable hardware like FPGAs can achieve 100% device peak tops. And we've actually proven that with the recent MLPerf submission, where we've actually achieved the exact same tops on the data sheet. And as a result, if you do an image per second divided by tops, we are ranking by far the #1, even against the state-of-art GPUs. Now, AI application is much, much more than AI. And while AI is very important, don't get me wrong there, but you're just moving the bottleneck to the other parts of the AI, and meeting the end-to-end requirements is the most critical thing to hit your AI algorithms into a production road. And then finally, we enable AI and software developers with Vitis AI that directly supports framework like TensorFlow and PyTorch. All right, thank you so much for your time, and I'm happy to answer any questions in the, question room. Thank you.